Okay, now we've been through some matrix arithmetic, addition, subtraction, scalar multiplication, matrix multiplication. This video is kind of easy subjects. We're just going to define some new terms that are pretty easy to grasp. First is the transpose. You just switch rows and columns. If A is m by n, its transpose denoted with the superscript t is then n by m. Each element of the transposed matrix is like the opposite of the original matrix A. Easy to just to view. This guy's transpose, it's a row, so his transpose is going to be a column. This guy's transpose is 3 by 2, so its transpose is going to be 2 by 3. This first column is this guy's first row, etc. For a square matrix, you just kind of flip it around so-called main diagonal. So this 2 will go down there, this 3 will go down there, etc. Transpose is pretty easy. Now that you know what a transpose is, if I have two column vectors, A and B, the transpose of A becomes this sort of a row vector. I can multiply them now that we've talked about matrix multiplication, and this is the total equivalent of the dot product. It's pretty easy to grasp if you've been through the rest of this so far. The zero matrix is easy to grasp. It's a matrix of all zeros. Any size, if you add a 0 to a matrix compatibly sized, you get the original matrix back, either left or right. Addition, if you subtract a matrix from itself or add its additive inverse, you get the zero matrix. If you multiply a matrix by the zero matrix, you get 0, assuming compatible size. So all those nice things, painfully obvious, it seems like. Some aspects of square matrices. The main diagonal is a big deal. It's this from top left to bottom right. So here is the main diagonal of this matrix. Square means m equals n. Triangular matrices. It's upper triangular if all these lower triangular guys are zeros. Everything below and to the left of the main diagonal, if they're all zeros, this is upper triangle. Everything above and to the right of the main diagonal are zeros, then it's lower triangular. Diagonal means everything except the main diagonals are zeros. So a diagonal matrix is both lower and upper triangular. Easy terms. A scalar matrix is a diagonal matrix where all the diagonal terms are the same term. It doesn't have a special symbol, so I'll just call it A here. It's square and diagonal, and all those diagonal terms are the same number. The identity matrix has its own letter, I. It's a scalar matrix where all those constants are ones, and it has these features. If I either pre or post multiply a matrix by the identity matrix, I get the original matrix. The I has to be of compatible size. So these are two different I's. In fact, here's an example. If I multiply this guy on the left by an identity matrix, I get the same matrix here. But if I multiply on the right, I need to use a 3 by 3. Here I used a 2 by 2. Here I need a 3 by 3. So these I's have to be compatible sized, but you always get back your original matrix. What does symmetric mean? It means the transpose of the matrix equals the matrix itself. Or the AJK term equals the AKJ term. You can view it as sort of the upper and lower triangles are mirror images of each other. This is a 2, that's got to be a 2. This is a 3, that's got to be a 3. That's a 6, that's got to be a 6. Main diagonal doesn't matter. It's flipped around the main diagonal. And of course, the transpose of any symmetric matrix, well, there it is. So of course, the identity matrix, the transpose of the identity matrix is just the identity matrix. It is a symmetric matrix. Well, here's what I meant to say. Any diagonal matrix is symmetric. Okay, those are some terms. Next, we want to talk about the arithmetic operation we haven't really talked about yet, division.